use MACLAURIN'S theorem to expand the function f of x is equals to sine squared x in ascending powers up to the term in x to power 6 up to the term in x to power 6, and hence evaluate the integral from 1 to 2 of sine squared x over x cubed dx. Now here, for you to evaluate this integral, okay, the first thing we need to write the MACLAURIN'S series, isn't it? So what is the MACLAURIN'S series expansion of a function f of x? When you want to expand the function f of x in the MACLAURIN'S series, you start from f of 0, isn't it? Are we together? Start from f of 0. Then after f of 0, we differentiate f of 0 once, you leave a space, isn't it? Then plus, you differentiate it for the second time, you leave a space. Then plus, you differentiate it for the third time, you leave a space. Then plus, you differentiate for the fourth time, you leave a space. Plus, you differentiate it for the fifth time, you leave a space. Then plus, you differentiate it for the sixth time, because you've been told up to the term in x to power 6, isn't it? Are we together? So here, let me create more space the other side so that I don't congest it. F to power 4, you leave a space. Then for the fifth time, you leave a space. Then for the sixth time, you leave a space. Now, when you differentiate it once, 1, meaning it is over 1 factorial, then your x is raised to power that 1, isn't it? When you differentiate it twice, then second derivative, meaning it is over 2 factorial, then your x is raised to power that 2, isn't it? When it is the third derivative, meaning it is over 3 factorial, then your x is raised to power that 3, isn't it? Are we together? Fourth derivative, it means it is over 4 factorial, then your x is raised to power that 4, isn't it? Fifth derivative, it means it is over 5 factorial, then your x is raised to power that 5, isn't it? Sixth derivative, it means it is over 6 factorial, then your x is raised to power 6, because we were told to reach that term in x to power 6. That's why we've gone up to the sixth derivative, isn't it? Are we together? Yes. Now, the first thing, the function, we have to get our function is f of x to be equals to sine squared x. Now, if you look at sine squared x, when you are going to differentiate sine squared x up to the sixth derivative, it is not going to be easy, my friend. Are you seeing? Yes. It is not going to be? It is not going to be easy. Because when you have this sine squared x, if f of x is sine squared x is the same as sine x, which has been squared, isn't it? So imagine differentiating this for the first time. You start with the outer function, the power 2, isn't it? The outer function, you let sine x to be t. It is like you are differentiating t squared, you get 2t, isn't it? Are we together? When you let sine x to be t, it is like you are differentiating t squared. So you get 2t, and the 2t, you put your value of t sine x. That's when you differentiate the outer function 2t. Is it there? Then you go to the inner function. The inner function is the t set, which is sine x, isn't it? If you differentiate sine x, you get cos x. Are you seeing here? So what do you have here? So you have the derivative is 2 sine x cos. Are we together? Now, if you look at this first derivative, if you try to differentiate it the way it is, it means you are going to use the product rule, isn't it? And when you use the product rule, it is going to generate more terms. Say there. Are you seeing that? Then if you differentiate for the third time, meaning you are making it more complex and more complex. So what it needs is that you must be someone who has deep understanding of trigonometry, isn't it? So it means this function differentiating for the first time is the simplest, and you get this, isn't it? So it means when I differentiate f of x for the first time, what have I found? I've found 2 sine x cos. Are we together? And you differentiate the outer function. If you let sine x to be t, it's like you're differentiating t squared, you get 2t. You are done with the outer function. You differentiate the inner function, which was t, and t was sine x, you get cos x. Then in the end, you substitute the value of t, which was sine x, isn't it? Then you get your 2 sine x cos. Now, when you look at that function, if you try to differentiate that function at that point, it is going to get more complex, isn't it? Now you just be observative. So what is 2 sine x cos x? That is the guy. That is sine 2x from trigonometry. 2 sine x cos x is the same as sine 2x. Differentiating sine 2x is very easy because you have the outer function and the inner function is just 2x. Are you seeing? But differentiating 2 sine x cos x, are you seeing that is complex? You are going to add more, generate more terms, isn't it? When you're using the product rule. So you express 2 sine x cos x in a form which is easier to differentiate. Are you seeing that? Are we together? Yes. You get? Sine 2x. So that is the reason why when you look at the function sine squared x, that function is the same as what? When you have sine 2x. Sine 2x is sine x plus x, isn't it? Sine 2x is, that is not going to help us. Move to this. When you have cos 2x. What is cos 2x? It is cos squared x minus sine squared x, isn't it? Then from here you now see cos 2x is equals to cos squared x in Pythagorean identity is 1 minus sine squared x, isn't it? See, that is cos squared x in Pythagorean identity. 1 minus sine squared x. Then it is minus sine squared x, isn't it? If you simplify this, you get 1 minus sine squared x minus sine squared x, you get minus 2, isn't it? So if you make this minus 2 sine squared x the subject of movement, see it comes this side. This side we have cos 2x. So minus 2 sine squared x coming this side, you have 2 sine squared x. Then the other side we have 1 cos 2x, going to the other side it is minus cos 2x. So if you divide both sides by 2, so you get a half. Meaning sine squared x is the same as a half minus half cos 2x. Are you seeing? Meaning where we have this sine squared x, it was the same as this, isn't it? So that the moment we differentiate this, if we differentiate this, what do we get? If we differentiate a half, we get 0, isn't it? If we differentiate negative half, it's a constant. If I differentiate cos 2x, I get negative sine 2x, isn't it? The outer function. Are you seeing that? Then if I differentiate the inner function 2x, I get 2. Are you seeing that? So that 2 this goes with the 2, negative goes with the negative, I remain with sine 2x. So that is what we have there. Are you seeing that? Are we together? Yes. So I'm saying you express it in a form which is easier to differentiate. This one was easier to differentiate when it is sine squared x. It's still the same as when you express it in this form, isn't it? Are we together? Then now 2 sine x cos x will be easier to differentiate when it is expressed as sine 2x, isn't it? Are we together? Good. So if you express it in that form which is easier to differentiate, you now just move. So here instead of 2 sine x cos x, we found it is the same as sine from trigonometry, isn't it? It's the same as sine 2x. Are we together? Good. So if I differentiate f prime, I get f double prime, isn't it? F double prime. So if I differentiate sine 2x, what do I get? You start with the outer function. The inner function is 2x. If you let 2x to be t, it's like you are differentiating sine t. So if you differentiate sine t, you get cos t. Serio? And cos t, what is your t? So your t is 2x. So you are done with the outer function. Then you go to the inner function, which is 2x, isn't it? What is inside that side, isn't it? If you differentiate 2x, you get 2. So it is the outer function times the inner function. You get 2 cos 2x. Are we together? Is that understood? Differentiating sine, when we are differentiating sine, we are not interested in what is inside it. Are you seeing that? If I differentiate sine, I get cos, then you put what was inside it, isn't it? Then it is cos 2x. Then now is when I differentiate what was inside. See there? The chain rule, isn't it? Are we together? Move to the next one. If I differentiate f double prime, I get f triple prime. If I differentiate cos 2x, remember, outside I have 2. So if I differentiate cos, without checking what is inside it, isn't it? If I differentiate cos, I get negative sign, isn't it? Then I put what was inside it was 2x. See, that one I've done with the outer function. Then I go to the inner function, which is 2. If I differentiate 2x, I get. Then you simplify. 2 times negative times 2, so you get negative 4. So you get negative 4 sine 2. So are you seeing when it was expressed in this form, differentiation becomes easier, isn't it? You move to the next one. F, fourth derivative of x, negative 4 is a constant, isn't it? if you differentiate sine 2x, so you get what you got there. See, this was sine 2x. See, when you differentiated it, you got this. Are we together? See, now we have negative 4, then if we differentiate sine 2x, meaning we are going to get what we got when we differentiated it, isn't it? We got 2 cos 2x, isn't it? See there? So 2 cos 2x times negative 4? Negative 8 cos? Are you seeing how this series are easy to work with? Because when you are differentiating something, sometimes you find that you've done it before. See there? Then you just put that value you got before. You move to the next one. The fifth derivative of x, negative 8 is a constant. When I differentiate cos 2x, what do I get? Remember, here is when I differentiated 2 cos 2x, isn't it? See there? So, negative 8 cos 2x can be written as what? So it is negative 4 times 2 cos 2x. See, negative 4 times 2 is negative 8. So it can be written in this form. So it is like negative 4, then if I differentiate 2 cos 2x, this 2 cos 2x, I've already differentiated and I got this. Are you seeing? Are you seeing how I'm doing this thing? So negative 8 cos 2x, if I want to differentiate it, negative 8 cos 2x, I already know how to get 2 cos 2x. So negative 8 cos 2x can be written in this form, negative 4 times 2 cos 2x, isn't it? So negative 4, then if I differentiate 2 cos 2x, the whole of 2 cos 2x, I got this. Are you seeing? I got negative 4 sine 2x. So in the end, what do I get? Negative 4 times negative 4? 16 sine 2x. Very simple by looking at what you did before. Instead of coming negative 8 cos 2x, you come here and say negative 8. When I differentiate cos, I get negative sine. Are you seeing this? I get negative sine 2x. What is inside? We are still not interested in. We are interested in the outer function first, isn't it? Then is when we go to the inner function. If I differentiate 2x, I get 2, isn't it? I get 2. So here, what do we have? Negative 8 times negative is positive 8 times 2, you get 16, isn't it? 16 sine 2x. Are we together? Then, we are done. We move to the last one. If I differentiate this, I get f sixth derivative of x. If I differentiate 16 sine 2x, see 16 is a constant. If I differentiate sine 2x, what do I get? Remember sine 2x was here. If I differentiated it, what did I get? 2 cos 2x. So 2 cos 2x times 16? 32 cos. Meaning it is easier to recycle what you've done before, isn't it? Are we together? Or it is simply coming here, 16. If I differentiate sine 2x, I get cos 2x. Then if I differentiate 2x, I get 2. So 2 times 16, 32 cos 2x, isn't it? Are we together? Yes. So from here, we don't need these functions. We need f of 0, f prime of 0, f down prime of 0, f triple prime of 0. Those are the functions we need, isn't it? Are we together? So you start, what is f of 0? F of x is sine squared x, meaning f of 0, where there is x, you put 0, isn't it? So where there is x, you put 0, you get f of 0, isn't it? So f of 0 will be sine squared of 0. So sine squared of 0 is like saying sine 0, which has been squared, isn't it? And what is sine 0? Calculator must be pi radians, my friend, isn't it? What is sine 0? See, sine 0 is 0. 0 squared is just 0. Then you go to f prime of 0. This one, isn't it? Are we together? We go to f prime of 0. So f prime of 0, this is f prime of x, meaning where there is x, we put 0, isn't it? So f prime of 0 is what? Sine 2 times 0 is 0. So sine 0 is 0. Are you seeing that? Are we together? Then you move to f double prime of 0. This term, f double prime of 0. So here we have f double prime of x, meaning where this x we put 0, isn't it? So f double prime of 0 is 2 cos 0. 2 times 0 is 0, isn't it? Are we together? Tuko pamoja? Yes. So what is 2 cos 0? 2 cos 0 is 2. So f double prime of 0 is 2. Then you go to that term, f triple prime of 0. F triple prime of 0. Here we have f triple prime of x, meaning where the x we put 0, isn't it? F triple prime of 0 is what? Negative 4 sine 0. 2 times 0 is 0, isn't it? Sine 0 is 0, meaning the whole of this goes to 0, isn't it? You move to f fourth prime of 0. This term, isn't it? And f4 prime of x is this. So where the 6 you put 0. f4 prime of 0 is negative 8 cos 0. 2 times 0 is 0. Negative 8 cos 0 is negative 8. You move on. F fifth prime of 0, the fifth derivative of 0, this. And we have this. F fifth derivative of x of 0, you get 16 sine 0, isn't it? Which is? 0. Then you move to f raised to power 6 of 0. The sixth derivative, 32 cos 0, isn't it? You put 0, you get 32. So the next step is now to substitute these values in the MACLAURIN'S series, isn't it? Substitute the values in the MACLAURIN'S. So the first value in the MACLAURIN is f of x, isn't it? So what is f of x? Sine squared x. So where there is f of x, we put its value, which is sine squared x, is equals to f of 0. What is f of 0? Meaning this term is 0. It is not there, isn't it? You move to the next one. F prime of 0 is? Meaning 0 times everything, the whole of this term will go to 0, isn't it? Then you move to the next one. F double prime of 0 is 2. So 2 over 2 factorial. 2 over 2 factorial. 1. 1 times x squared, so you remain with x squared. Are we together? We are done with this term, isn't it? We move to the next term. F, third derivative of 0 you found to be 0 times everything, the whole of this term will go to F, fourth derivative of 0 you found to be negative 8. So negative 8 over 4 factorial is negative 1 over 3. Some of these things, what do you have? Negative 1 over 3. So we have negative 1 over 3 times x raised to power 4, isn't it? Negative 1 over 3 times x raised to power 4. We are done with this term, isn't it? F fifth derivative of 0 you found to be? So 0 times everything here, meaning everything here will go to 0, isn't it? Are we together? Then f6 derivative of 0 you found to be? 32. 32 over 6 factorial? 2 over 40? 2 over 45. So 2 over 45 times x raised to power 6, isn't it? So it is positive 2 over 45 x raised to power 6. So have you seen, we've expanded sine squared x in the MACLAURIN'S series up to the term in x to power 6. Power? This. Or it is here. This is x to power 4. This one. Very good. So we have, this was the where we have f4 derivative, negative 8. Yes, negative 8 over factorial, negative x to power 4. Very good. Are we together? So you've expanded sine squared x in MACLAURIN'S series, and this is the expansion we found, isn't it? Now, having found this expansion, you've been told to use it to evaluate this integral, isn't it? You've been told to use it to evaluate this. Are we together? So when you are evaluating the integral from 1 to 2, in the numerator we have sine squared x over x cubed dx. What do? You substitute the value of sine squared x, isn't it? And the value of sine squared x we found to be this in the MACLAURIN'S series, isn't it? Are we together? So we do the substitution. We have the integral from 1 to 2. In the numerator we have sine squared x, which is the same as what? X squared minus a third x to power 4 plus 2 over 45 x to power. Then the whole of it is divided by x to. The whole of it is divided by x to power. X to power 3. Then dx. See now what we do. What is in the denominator is the common denominator, isn't it? Meaning the common denominator divides everything in the numerator. Are you seeing that? The common denominator divides everything in that. So what do we have? We have the integral from 1 to 2. X squared divided by x cubed. See, you have 1 over x. Isn't it? So this is x squared divided by x cubed. So you get 1 over x. Huh? Then here we have minus a third in there, minus a third there. X to power 4 divided by x cubed, so you remain with x. See there? Here you remain with x in the denominator, here you remain with x in the numerator. Is that okay? X cubed, here of course we write our 2 over 45. 2 over 45, then x to power 6 divided by x cubed. X? Lots of indices, x cubed. Somebody saying x cubed squared. X to power 6 over x cubed. Lots of indices, same base with the division sign, you do what? Isn't it? X cubed. So have you seen with what I read of that denominator, isn't it? Because this is like x, this is like x squared over x cubed, we got 1 over x. This one is like a third x to power 4 over x cubed, we got a third x. That one is like 2 over 45 x to power 6 over x cubed, we got 2 over 45 x cubed, isn't it? Then, the whole of that we are integrating with respect to x. Good. So start. If you integrate 1 over x, what do you get? ln of x, isn't it? So if you integrate 1 over x, you will get the ln of x. That is like saying integral of dx over x is ln of x, because dx multiplies everything inside, isn't it? See dx times this, you get dx over x. If you integrate dx over x, you get ln of x. Isn't it? Are we together? You move to the next one. If I integrate negative a third x, see that is now a polynomial. So negative a third is a constant. If I integrate x, I get x squared over. That is what I get. I get x squared over 2. So in the numerator, negative a third divided by 2, because 2 is in the denominator. Negative a third divided by 2, you get negative 1 over negative 1 over 6, isn't it? Are we together? Are we together? Negative 1 over, so that is negative 1 over 6x, x squared. If you go to this x cubed, this is a polynomial, isn't it? So we have 2 over 45 outside, then inside, if I integrate x cubed, see I get x raised to power 4 over 4, isn't it? So 2 over 45 divided by 4, because 4 is in the denominator, isn't it? Is that okay? Yes. 2 over 45 divided by 4? 2 over 90. 1 over 90. Good. You get 1 over 90 times x to power 4, isn't it? So it is plus 1 over 90 x raised to power 4. Then you put your limits of integration, isn't it? Your limits, the lower limit was 1, the upper limit is 2. So what do? We substitute upper limit minus lower limit. Upper limit, where there is x, you put 2. Where there is x, you put 2. What do you get? If you substitute 2 where there is x, what do you get? Substitute 2. When you are doing substitution, we don't come and write at ln of 2 minus 1 over 6, 2 squared. That is waste of time. Substitute 2 in the calculator and write the answer direct. You don't do that there. That is the work of a calculator. Substitute the upper limit 2. ln of 2. Substitute 2 in the calculator. So you found 0.2, 0.4, 0.204, 5 decimal places. 26. Then substitute the lower limit 1. When you substitute 1, ln of 1 is always 0. The log of 1 is always 0, isn't it? Substitute ln of 1 minus 1 over 6, 1 squared. 1 raised to any power is just 1, isn't it? So this is just negative 1 over 6 plus 1 over 90. What do you have? Negative 0.1. 5 decimal places. 6. So this negative into negative is, so you are going to have minus negative. So that is going to be positive. So this and that, what do you get? What do you get? 0.20426 minus negative 0.15556. What do you have? 0.3? 59881. Are we together? And you have evaluated that integral. You have evaluated that integral.